Ladies and gentlemen, greetings. In this video I would like to talk to you about related rates and their applications. Things we will cover will include changing volume and surface area of a sphere. We're going to use an air balloon as an example, but this is going to be fairly different, so please stick around. After we're going to investigate spherical behavior, we're going to take a look at how fast the distance changes between two moving objects. Once we'll be done with that, it will be only a logical extension of that to move on to the inverted cone water tank problem. Once we will tackle inverted cone water tank problem, we'll be prepared to talk about formation of a pile of gravel or whatever objects that are being piled up. Once we're through with that, then we're going to discuss sliding ladders, their behaviors, and then we're going to top things off by the problem of a rate of a rotation of a tracking projector. So stick around. Oh, and before I forget, a piece of formality that we do for each video, in order for you to get the most out of this bit, you must be familiar with the rules of differentiation. You must possess a knowledge of basic geometry, you must have a good working understanding of implicit differentiation, and it will also help if you will bring to the table a pinch of cleverness and a ton of attentiveness. Alright, so let's get started. So let's start our discussion of spherical objects in the nature by considering the following examples from agricultural industry. Pomegranates, very delicious. Oranges and grapefruits, even tomatoes, they all approximate as a sphere. And even turning to the human body as an example, we don't have to look too far, no pun intended, before we will see a human organ that could very easily be approximated as a sphere. So in order for us to arrive to some very interesting engineering results, it would be very helpful to recall these two formulas from our geometry days, namely the formula for the surface area of a sphere, as well as the formula for a volume of a sphere of a radius r. So now let's do what we came here to do. Suppose we have a problem in which the radius of a sphere is increasing at a rate of 1 meter per second. And we are asked to find the rate at which the volume is increasing when the radius becomes exactly 20 meters. Okay, so let's make ourselves a diagram. So let's suppose that we have a yoga ball, or better yet, an air balloon that's going to allow us to visualize this problem, and suppose that this is the sphere that we're talking about. Let's make ourselves a list of what we know and what we don't yet know, aka something that we're going to solve for. So here we're going to type in a column of knowns. So we know that at some point in this problem, the radius of this flying balloon will going to reach 20 meters. We also know that throughout the problem, rate at which the radius is changing remains constant, 1 meter per second. All right, please don't miss the forest for the trees here. Rate of change of radius remains constant throughout the problem, and the radius obviously starts to grow, because when the balloon is deflated, right, it's going to be much smaller. And as the time expands, it's going to grow radially in all sorts of directions. And at some point in this problem, the radius is going to become 10 meters, 11, 12, 15, 18, 20, maybe even more. Who knows? But the point is that this value is a specific case in point. Okay, so these are knowns. Now, what don't we know? We are asked to find rate at which the volume is increasing. Sounds like V prime is going to be a question mark. And this, my friends, is where implicit differentiation is going to come into play. If we're going to take our expression for the volume and apply implicit differentiation on both sides, so if I will leave verification of a product rule to you, our final result is going to look like this. V prime is going to equal to 4 pi r squared times r prime. Now let's put check marks next to everything that we know. Do we know the value of pi? Well, you bet we do, right? That's a check. Do we know the value of r, at which we are asked to figure out the value of v prime? Well, surely we do, right here. R is going to equal to 20. We merely have to plug it in. Do we know the value of r prime? Yes, we absolutely do. It's right here. So without any further ado, we readily have an expression for v prime of this form. 4 times an approximation for pi times the 20 meters squared times the value of r prime, which is 1 meters per second. Please don't be flamboyant with units, because units, as you will see in a second, are going to be a very important sanity check. Okay, so we're going to multiply it by 1 meters per second. So if we'll perform multiplication, we're going to receive something of this ilk, 5024 meters cubed per second. Notice meters squared times the meters will going to become meters cubed, and per second. It makes a lot of sense. Why? Because these are the units of the volume change per second. Volume on the top, seconds at the bottom. Okay? All right, so this is basically part one. Next I will ask you, can the sphere only be inflated? What will happen if the sphere deflates? And you could tell me, of course, it could be deflated. What kind of question is that? But notice, if it deflates, its internal volume will going to go down. Yes, that's correct. And we can very easily figure out rate of change of the volume at any given radius we want using this formula. We've done all the work now. Except I want to present a different spin on this problem for you. So let's consider a problem in which indeed the balloon gets deflated. And more specifically, its radius is decreasing at the constant rate of 3 meters per second. And as a deliverable in this problem, we are asked to find the rate at which, attention, surface area decreases when the radius reaches exactly 10 meters. Okay, so here's the diagram for the situation that we're facing now. The volume of the sphere goes down, right? And as a consequence, the rubber coating here shrinks. So as before, let's make ourselves a list of stuff that we already know and stuff that we yet to figure out. What do we know? We know the fact that at some point the radius is going to reach the value of 10 meters. Check. This is the radius of our interest. We also know that the balloon is shrinking. Therefore, the rate of change of its radius must be negative. Remember that. It's going to save you a lot of hassle. Increasing, the sign is going to be positive. Decreasing, the sign is naturally going to become negative. And our goal, therefore, would be to figure out an expression for A prime. Well, fortunately, a few minutes ago, we've seen the formula for the area of a sphere. That tells us that the area is proportional to 4 pi r squared. At this point, guys, I recommend you pause the video. If you feel comfortable enough, then please don't be shy. While you have this video paused, go ahead, not only apply differentiation, but try to solve for a numerical value of A prime. And once you're going to come back, we're going to compare notes in a moment. All right, pause me and then come back when you're ready. Hey guys, welcome back. Here's what I got for implicit differentiation. The actual calculus part here is going to be fairly straightforward. It's going to be application of a power rule. And while we're at it, I wanted to point out to you guys that this is, technically speaking, this is a product rule at play. So if you're going to expand this product rule, you're going to land with something like this. And an expression for A prime will going to be given by the formula 8 pi r times r prime. Let's whip out our markers and give check marks to the values of variables that we know. Do we know pi? Well, laughable, right? Of course we do. Do we know the value of r? Yes, of course we do. And do we know the value of r prime? You bet, right here. The value of r prime is given to us, so all we have to do is literally plug and chug. So the value of A prime is going to roughly equal to 8 times 3.14 times 10 meters times the value of r prime, or dr dt if you would like to call it that. All right, so if we'll do the algebra, this is where we're going to get our final answer. Guys, I cannot stress to you enough how many times in the past on my exams and homeworks, units saved the day for me. Please notice that meters times meters will going to give us meters squared, and division by the seconds we're going to just carry right over. All in all, do these units make sense? Well, I'll let you be the judge. Upstairs we have area, downstairs we have time. Area per time, that makes sense. That's the rate of change of A. All right, and now to the mother of all of the spherical related rate problems. That's going to unify previous couple of examples into one. Suppose we have a problem that tells us the rate of change of the sphere, and in return it asks us to figure out the radius at which the rate of change of volume of the sphere is equal to the rate of change of the surface area of the sphere, right? So let's recap what we know and what we don't know. We know that the rate of change of the radius is given to us, and the actual numerical value will going to become a little bit inconsequential, as you will see in a second. But we also know from previous setup that we have an expression for the rate of change of volume, V prime, and we have a rate of change of surface area, A prime. We have formulas for both of those guys. Now, we are asked to find the radius at which V prime equals to A prime, like this. right? So in order for us to solve this problem, we have to make left-hand side equal to the right-hand side. We're going to have an equation of this sort, and then we just algebraically need to solve for r. Please notice that 4 and 8 could cancel out, pi's go bye-bye. R primes, they are not going to be zeros, so they could be canceled out. And the value of r is also not going to be 0. Therefore, we can very easily arrive to a numerical answer of r equals to 2 centimeters. At this point, ladies and gentlemen, I want to draw your attention to the fact that we can validate our numerical answer, our analytical answer, in a graphical way. If we were to go to Desmos and to plot v prime and a prime, red graph represents the function for v prime, and the blue graph represents the function for the rate of change of area. And guess where do they intersect? They intersect at 0.2, 144 pi. Well, this x address of this point of intersection is indeed our answer. So how cool is that, right? Also, please remember this number, 144 pi. We're going to see that in just a moment. Technically, this problem is solved. And guys, as I stress in class on many occasions, after you're done solving the problem, please do yourself a favor, go back and plug in this value. Make sure you didn't mess up accidentally somewhere along the way. So if we're gonna go back to our formulas for a prime and v prime and plug in r equals to 2, we're gonna very quickly discover that a prime will gonna equal to 16 pi times 9. Oh, by the way, units work out, right? Centimeters squared, aka area per time. That makes sense. That's in line with the a prime. And while we're at it, v prime is going to equal to, look at that, 16 pi times 9 centimeters cubed per second. Again, units are just paying us compliments in this case because units also are consistent with the physical quantity that we're looking at. The rate of change of a volume is given in terms of volume per unit time. All right, well, that's aesthetically pleasing. But without us maybe fully realizing this, we can now definitively answer even the bigger question that's going to relate the rate of change of a volume and the rate of change of a surface area. So for example, we can answer the question at what radius volume will change twice as fast as the surface area. Or perhaps we want to know at what radius volume changes exactly 5 or maybe even 9 times faster than the rate of change of a surface area of a sphere, right? Well, good news is we already have vast majority of work done for ourselves. We then just have to set v prime equals to k, some coefficient of proportionality, times a prime, something like this. And then from there follow our nose. Here's our left-hand side and right-hand side that promptly reveals that radius of our interest is going to equal to 2k. Let's put a couple of numbers on the canvas here. Suppose we're wondering at what point volume changes twice as fast as the surface area. Well, use your formula. 2 times k, this unit of proportionality, 2 replaces k, and our answer is staring us in the face, right? Well, suppose we are curious then at what point volume grows 5 times faster than the rate of change of the surface area. Well, that's at the point where radius is going to equal to 10. Suppose we want to know at what point volume grows 9 times as fast as the surface area. Well, okay, that's the equation we'll need to solve, and it's going to promptly yield us to the fact that r will going to have to be 18 units, right? Okay, maybe, hey, we were just considering growing volume. What if volume is shrinking? Maybe we want to know how fast the volume drops as the area shrinks. Say we're curious at what radius the rate of growth of volume is going to equal to the 10th of rate of growth of the surface area, like this, right? Well, that's going to yield us to the fact that r will going to have to equal to 0.2. If we want to know at what point rate of change of v is going to equal to 100th of a rate of change of a, that's also easily arrangeable like that, right? But I think you guys see the point here. All right, so that's the story of related rates for a spherical object.